Hello everyone, this is lecture 9 of course BE544. In the previous lecture, we ended our discussion by talking about something called overfitting and underfitting. And we mentioned that when there is a gap between the training and validation, this can suggest the concept of overfitting if the training surpasses the validation, and if the validation surpasses the training, this is called underfitting. So overfitting occurs when a machine learning model learns the details and noise in the training data to such an extent that it negatively impacts the performance of the model on new data. So the model had learned on some sort of data that contained noise or outliers. And this typically happens when the model is too complex with too many parameters relative to the number of observations. For example, you can build a very complex model with just 10 instances. And as a result, the model fits the training data very closely, and this will capture both the underlying patterns and the noise. As mentioned, to sign that there is an overfitting, you need to check that there is a significant gap between the training performance and test performance. For example, the model can show very high accuracy on the training set, but much lower accuracy on the test set, as we show in the previous figure. And this indicates that it's not generalizing well to the new data, but is instead memorizing the training data. On the other hand, underfitting occurs when a machine learning model is too simple to capture the underlying structure and patterns of the data. This means the model performs poorly on both the training data and test data because it fails to learn the patterns and features in this data. And also there is a sign that there is a poor performance on the training set, which usually translates to poor performance on the test set as well. But the test set or the validation set will surpass the training set. And this will indicate that the model is not flexible enough to capture the complexities of the data. There are many causes for overfitting. These include that you are using a model with too many parameters. Second, having insufficient training data, small number of instances, and including too many irrelevant features that introduce noise and outliers. And to overcome overfitting, you can apply the number of parameters and the complexity of the model using something called regularization. There are many regularization techniques such as L1 regularization, L2 regularization, and dropout. You can apply also cross-validation, where we mentioned in the previous lecture that you can split the data into portions or groups or folds, where the training applies on k-1 folds and the validation will be applied on the remaining fold. Also, you can augment the training data using something called data augmentation, and you can also use early stopping. As we mentioned in the previous lecture also, early stopping stops the training process when there is no increment in the performance for a set of iterations or epochs. Underfitting can be caused using models that are too simple or not including enough relevant features or having high bias, which assumes strong but simplistic assumptions about the data. And this is the opposite of overfitting. And to overcome underfitting, you can increase or upgrade the model to be more complex or use more sophisticated algorithms. You can also add more relevant features. You can reduce the regularization strength. You can also train the model for more epochs to learn more complex patterns during the training process. And the mid between overfitting and underfitting is the fitting. So you need to achieve a balance between overfitting and underfitting for developing a robust model. This is referred to something called bias variance trade-off. Models with high bias is called underfitting, where these models are too simplistic, and models with high variance or overfitting are too complex. So you need something between both of them, with low bias and low variance, which can generalize well to the new data. To find that you are selecting the good model and there is no overfitting and underfitting, or in another meaning with a low bias and low variance, check the model curves, check the gap between the training and validation or the training and testing. If the gap is too small or not significant, and both of the training and testing or training and validation are high, for example more than 90, then you can say the model is fitting and can generalize well to the new data. So to summarize the techniques to fight and overcome overfitting and underfitting: to overcome underfitting, add more complex model, increase the number of parameters, reduce the regularization, add more features to the data, and if you added more data, this may not help. To overcome overfitting, you need to decrease the complexity of it by making it more simple, add regularization as mentioned L1 and L2, use a smaller quantity of features, and add more data. As mentioned, regularization techniques are essential in machine and deep learning to prevent overfitting and improve the model's generalization. These techniques will help by adding some constraints or penalties to the learning process. The commonly used techniques are L1 and L2 regularization, where L1 regularization is called lasso, where it adds a penalty equal to the absolute value of the magnitude of the coefficient. As you see in that equation, it gets the magnitude of the coefficient and apply the absolute value of it, and then apply by the regularization coefficient or parameter or factor, and add that to the cost function, which will be used later to update the weights. By doing that, this can lead to sparse models where some coefficients become zero, and this can be effectively performing feature selection. L2 regularization or reg, this will add a penalty equal to the square of the magnitude of coefficients, distributing the error among all coefficients. So you are getting the square of the weights and multiplying by a parameter called lambda, and this parameter can be considered as a hyperparameter that can be tuned, and by combining both L1 and L2 regularization, we can call that elastic net regularization, and this will balance sparsity and coefficient shrinkage. Another regularization technique is called dropout, and this technique is used primarily in deep learning, and it's applied only during the training process. So what happens in the training process by introducing the dropout? You are selecting random neurons and ignoring it. If you remember the fully connected or the dense layer, where each neuron is connecting to all of the previous neurons, like here. But if we introduced dropout, in that case, some neurons will be ignored randomly, and this will prevent the network from becoming too reliant on particular neurons, and it can promote robustness and prevent overfitting. Data augmentation is an approach to increase the size and the number of training samples artificially by creating modified versions of the images. So we have the original image, and we can apply data augmentation techniques such as rotation, flipping horizontally and vertically, scaling in both directions, grouping, color changing, such as increasing the brightness or decreasing the contrast. As you see in the example, the original sample is flipped horizontally, vertically, rotated, zoomed, shifted in both directions. So from a single instance, you got more 6 instances. But you must be aware of something. There is something called data leakage. Data leakage means some samples from the training went by mistake and without intention to the testing. How this can happen? Assume you have data like that, and this data is not enough for a deep learning model to overfit, so we decided to apply data augmentation. So we took the first instance and applied data augmentation by, for example, rotation or flipping, and the same for the second, the same for the third by zooming, and for the last by shrinking. And now we need to split the data into training and testing. So you will say that we have now 10 instances. If you decided to split the data randomly, for example, the training set will be Z1, Z1, Z, 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 and Z, 6 instances, and the testing set will be the remaining Z, the circle, and the triangle. So if you look carefully, you will notice that an augmented sample found in the testing set and also its original or augmented version is found in the training set. This is called data leakage. And also here there is a version which is similar to that version. So when the model will learn the patterns of that circle, it will find again another augmented version of that in the testing set, and with a high percentage will classify it correctly. And as we noted, testing sets or data should be unseen, but this one, that, and that are seen in the training process. So to overcome data leakage, when you are going to apply data augmentation, it's recommended to split first and then augment the training subset. Another technique is called batch normalization. And batch normalization will normalize the inputs of each layer to have a mean of 0 and a standard deviation of 1. And this in many cases will help stabilize and accelerate the training process. So if we have samples or distribution like that, by normalizing it to a mean of 0 and a standard deviation of 1, it will be spread along the axis where the model can easily or better classify between the samples. 3 more techniques. Noise injection. And noise injection means you are adding random noise to the input data or weights during the training process, and this may prevent the network from relying too heavily on specific patterns, and it can force the model to generalize better. Second, gradient clipping. It involves setting a threshold to gradients during the backpropagation process to prevent exploding gradients. So you are setting a threshold or boundaries to limit or clip the gradient values. In simple methods such as bagging, posting, and stacking, you can combine predictions from multiple models, and this can improve the robustness and generalization. For example, you have 3 models where the 3 models are trained on the same data or the training data, and then you are getting the output of each model. So now you will have 3 outputs. You can then apply majority voting between the 3 of them to get a final output. For example, 2 of them says that instance is a tumor and 1 says it's non-tumor, so the final output will be tumor. So let's apply some of these techniques in our code and update our previous code to a newer version. If you remember, in the model we created in the previous lecture, we created a set of conv, max pooling, cascaded layers, then flattening, then 3 dense layers where the last layer is the output layer. Here we introduced dropout layers between the flatten and the dense, and between the first dense and second dense, another dropout layer with a value of 0.5, and this means dropout of 50%, and this means you are dropping half of the neurons randomly between these two layers. Then we kept the compilation, verbosing, and return as it is. We reduced the batch size from 64 to 32, and instead of loading all of the images in the XY lists, as we saw in the previous lecture, we applied a new approach. And before introducing that approach, let's see the disadvantage of the previous approach. Assume that you have 10K images, so you are going to load 10K images in a list called X, and you are going to store that X in the memory. So you are consuming most of the memory, especially if you have a small size memory, for example 16 gigabytes, and wasting that storage during the training process or during the execution of the code. So instead of loading all of the images first, you can load the images which are required to be used. So instead of loading 10K or 1000 or 500 images, you are loading only the number of images corresponding to the batch size or what's required by the model. So here we can use a function called flow from directory that takes the directory or the folder and the batch size and the type of the class that we are targeting, whether it's a sparse or categorical, and if you need to shuffle or not, and automatically it will load the X and labels or the images and corresponding labels to the model. Also, it will convert from strings to one-hot encoding because you are defining the class mode as categorical, and it will load a shot by a shot because you are defining a batch size here. This function can be found in a class called image data generator. So we first created image data generator for the training, and another for the validation, and a third for the testing. And we noted that when you are loading the data, rescale it and normalize it. So if you remember in the previous code, we have normalized the data after loading it. But here we are informing the function to normalize it automatically once the data samples are loaded. We made the same for validation and for testing. So now we have 3 generators. What about that? As we mentioned, the flow from directory function will require a folder to load data from it. So we need to extract these folders, training, validation, and testing, so the function can load from these folders. So simply, there is a package called split folders where you can install it using pip command, pip install split folders, and import it. Then you can use a function called fixed. You define the base path of it, of the data, and define the output path where do you need the data to be stored, and define the required sizes to be splitted for training, validation, and testing. So it will take 2K for training, 500 for validation, and another 500 for testing. And we need to emphasize that fixed numbers 2K, 500, and 500 will be applied on each folder from that folder. So in our dataset we have 4 classes, so it will take from each class or each folder 2K for training and 500 for validation and another 500 for testing. So the accumulation based on the 4 classes will be 8K for training, 2K for validation, and 2K for testing. And we added that condition because we need to split the data once. It checks if that folder is not created, it will create it. After that, we got the model with the same optimizer and verbose to 1. Then we applied the fitting with the same parameters, but instead of passing the x and y preprocessed lists similar to the previous code, here we are passing the train generator. So you have two options. You can pass the x and y manually or pass a generator. The generator will flow from the directory and get the x, y and process them and provide them to the model. The same for the validation data. We are passing the validation generator. After that, we are loading the best checked weights because we are using here the model checkpoint. Then for the 3 generators, we are calculating the performance. And as we mentioned, the loss is the first metric, where the rest will be similar to the order that we defined in the metrics during the compilation of the model. After that, we plotted the training and validation curves for the loss and accuracy, and we added a line here before the show function to save the figure if you need to save it for further processing or usage. After that, we plotted the confusion matrix using the same approach, but here for the y-actual, because we are dealing with the test generator, we are getting the classes from it. So you are using the classes attribute from the test generator that we created earlier to get the actual y. And for the prediction, you are applying argmax as discussed to get the y predicted. Then you get the confusion matrix and display it. By executing the code and comparing both before dropout and increasing the data for the previous code, we noted that there is a significant portion between training and validation, and this is called overfitting. But the overfitting is reduced when we added data dropout, so the gap is reduced and the overfitting is reduced. But this is not sufficient. You need to improve the model more and more to reduce that gap and increase the performance. And these are the results. You will see that the training accuracy reached 95%, while the validation and testing is stuck at only 70%. And the same for other metrics. There is also a gap which can be overfitting. And we learned how to read the confusion matrix. You need first to define the true and predicted. Then for that number, we can say there is 375 actual carcinoma in situ and that are predicted correctly, while there is 64 actual normal cases that are incorrectly predicted to be benign. In that code, we applied more data manually by incrementing the number of samples to be extracted. As we said, we have 8K for the training, but for the previous code, we got only 1200. We can also improve that code by introducing data augmentation. So to apply data augmentation, we kept the code similar to what we discussed, but what is modified here is that in the image data generator for the training, we applied the ranges of the augmentation techniques. So we said you can apply rotation up to 45 angle and width and height shifts up to 0.1 or 10%, and the same for shear and zoom, and allowed it to apply horizontal flipping and vertical flipping. And this doesn't mean that all of these will apply on each image, but these hyperparameters or ranges will be applied randomly. The rest of the code is the same, and we applied data augmentation in the training only, not the validation, not the testing, because we need to train and learn the model, and this happens only in the training process. Then we fitted or trained the model and did the same for the rest of the code. If we compared without data augmentation and with data augmentation, we will find that the gap is reduced between the training and validation. So data augmentation helped to reduce overfitting. And the gap between training and validation is not significant enough to say that there is underfitting, because the validation surpassed the training. And if you look at the evaluation metrics, you will find that the accuracies for the training, testing, and validation are so close, although the results are lower than 85 or 90. And the same for the confusion matrix. You can say there is 14 actual benign cases that are incorrectly predicted to be normal. If you remember that we added a callback function called TensorBoard to our callbacks, and we said that tool can provide many visualizations to our model. And if you don't have the TensorBoard callback installed with the TensorFlow package, you can install it using the pip command pip install TensorBoard and run the code to install that visualization toolkit. Then how to access the TensorBoard? You need first to define the TensorBoard in your code and define the log directory. In our case, we are storing in history, simple CNN augmentation, and another folder called logs, which is that folder. So we can simply open the terminal and then write TensorBoard 2 dashes log dir and then define the folder that contains the logs. If you open that, you will find two folders, training and validation. So we need to define that folder. So here we will write logs and press enter. It will start to operate, and once it's ready, it will give you a link to open it, or it can open automatically. If it didn't open, you can simply copy that link in your browser. As you see here, it will open that UI, user interface. You can go to scalars and it will display the different performance metrics that you mentioned in the metrics list. You'll find here the false negative. If you scroll down, you will find the categorical accuracy. As we see here, you can maximize it and move to any data point to the corresponding epoch so you can find the corresponding value. So for example, at that point, as you see, there's a step of 113 and the value is about 0.74 for the training and 77 for the validation. You can also smooth that curve by decreasing or increasing the smoothing factor. As you see here, if you need a smoothed line between the training and validation, so it will decrease the opacity of the actual training and validation curves and will present the smoothed line. You can also uncheck each of the training and validation to hide it, as you see here, and for the training, as you see here. The same can be applied for the loss. You can maximize. You can also zoom in and zoom out by clicking with the left mouse and selecting a region to zoom it, and you can return by using the fitting button here, as you see. And if you need the y-axis to be a log scale, you can toggle that button. Now it's log scale. Now it's returned to the original value. The same for other metrics. So in that lecture, we have defined a set of techniques to fight and overcome the issues of overfitting and underfitting. For overfitting, such as data augmentation and reducing the model complexity, and we applied a code with a dropout and increased the number of samples to 8K for the training, and then applied data augmentation, and we saw that data augmentation helped to reduce the overfitting. And finally, we introduced the TensorBoard and how to access it and then navigate to the different scalars or plots.